In this screencast, I'm going to show some simple examples of problems with numerical precision in computer arithmetic, and show why it's important to have a system like Mathematica if you want to be able to get the right answer. Let's start by doing an example in a different piece of software. Here I have Microsoft Excel. But I should make clear that what I'm about to show is not exploiting some bug in Excel or some error by the programmers, but something intrinsic to computer arithmetic. I'm going to start with a simple piece of input, 0.2, and I'm going to pass that through a formula. My formula is take 11 times that piece of input and subtract 2. And we get back to 0.2, as that is a fixed point of this formula. I'm now going to copy that formula down so that I'm passing the result repeatedly through the same formula. As you would expect, we continue to get 0.2. But after a while, something interesting happens. And very quickly, we get a result that is a long way from the correct value. The reason is that 0.2 cannot be held exactly in binary, in which Excel is doing its arithmetic. In fact, it's an infinitely recurring sequence of bits. And so the only way to hold 0.2 is as an approximate value of around 0.2 plus about 10 to the minus 16. And each time we multiplied by 11, that error grew and grew and grew until it overwhelmed the result. Okay, so let's look at what's different in Mathematica. As I said, the error is intrinsic to computer arithmetic. So we find if we set up the same problem in Mathematica, here's our formula, and here we're going to specify that we apply that formula to 0.2 30 times, we get the same or similar behavior. But the difference in Mathematica is we do not have to accept the approximations that are defaulted by the computer. Instead of accepting 16 decimal places of precision to this initial value, I could specify 30 decimal places. And now, when we repeat the computation, the error has been pushed sufficiently far away that we can get reliable results for much, much further. And indeed, if necessary, we could do 300, 3,000 or 3 million decimal places to control the amount of error in the initial input. But there's something slightly more subtle that is much more important going on. You'll notice that the first results, it reports many digits of answer. But towards the end of the computation, it's reporting very few digits. The reason is that Mathematica not only is able to control the amount of error, but it can track the propagation of the error. So it reports many digits at the beginning because it believes it can justify all of those digits. But towards the end, as it tracks the potential growth of the error, it can only guarantee one decimal place here to be correct. And indeed, if we ask it what it knows about each of those numbers, we can see 30 decimal places were guaranteed to be correct. But at the third last answer, only about one decimal place was guaranteed to be correct. And indeed, Mathematica knows that the last two, there is nothing reliable about these results. So this allows you not only to be able to control errors, but also to have confidence in the results that come out. Now let's look at a slightly more involved example. The Hilbert matrix is a classic example of an ill-conditioned problem, and I'm going to enter a simple 10 by 10 Hilbert matrix here. I've got a table whose entries are 1 over I plus j minus 1. If we look at that as a matrix, you can see that it takes the structure starting with 1 in the top left corner, with diminishing values towards the bottom right. This is well known for having a very high condition number and being very difficult to work with numerically. However, in Mathematica we can hold these numbers in an exact representation, where a 19th is held as a fraction rather than as a decimal expansion. And this makes it possible for us to do things like taking the inverse of that matrix in an exact way, and here we get the integer results out, which we can see are quite large compared to the original matrix. Now, if we were to emulate the way that most numerical systems work, the many matrix laboratories available, we find that it's very difficult to get the correct answer. Here we're taking an approximate version of that matrix, each number held only to 16 decimal places, the typical working precision of these systems. If you now compare the inverse of the exact input with the inverse of the approximate input, we should get the same results, and so the difference should be 0, and the maximum difference should be 0. Well, Mathematica warns us that the approximate version simply doesn't have enough working precision to give us a correct answer, and we find the error of working with these machine precision numbers is very large, around 10 to the 8. Just as before, we also have the choice in Mathematica of working with high precision numbers. So let's see the effect of doing that. Here is a version of the matrix where each of the numbers is held correct to 30 decimal places. Now let's look at the same comparison again. We'll take the maximum, the inverse of the exact, with the inverse of this new approximate to 30 decimal places version. Now, with this extra working precision, we can get the correct result, which is 0. And it's telling us here that this 0 is guaranteed correct to 18 decimal places. So while we started with 30 and we've lost lots of working precision because of the difficulty of this problem, we still have plenty left to give us a reliable result. While numerical errors will show themselves under different computations in different systems due to the way that they're implemented, these problems exist somewhere in every numerical system. But only with Mathematica can you have the range of computational tools from exact to high precision arithmetic and precision tracking to not only get the right results, but know that you've got the right results.